Chapter 8 begins the mole. Chapter 8, Section 1 tells us that a mole, which is abbreviated MOL, refers to the amount of substance. The mole is based off of carbon-12. That is how many atoms are going to be in 12 grams of carbon-12. That was the standard that was chosen off of the periodic table to base the mole off of. One value that you will need to know is called Avogadro's constant. It's 6.02 times 10 to the 23rd particles in every 1 mole. Now that could be atoms in a mole, molecules in a mole, or formula units. When we are talking about molecules, those are things that are covalently bonded to each other. Our textbook refers to ionic molecules as formula units. These are the conversions that we're going to be doing. When given moles, and this was just a value that I made up, you will use Avogadro's constant to figure out how many atoms are within those particular amounts of moles. So for this one, we have 2.66 moles, and I'm going to set up Avogadro's constant, 6.02 times 10 to the 23rd atoms in every 1 mole, and by multiplying those values together, that will allow my mole units to cancel and will tell me how many atoms that I can get from that. You can also do the reverse. You can start with atoms and use Avogadro's constant to find out how many moles that could make. So with atoms, you still use the constant for Avogadro, but we will flip it upside down. Okay, this time we want atoms units to cancel and our end units to be in moles. So we want to have 2.54 times 10 to the 24th here divided by 6.02 times 10 to the 23rd, and that will allow our atoms units to be canceled. We could do the same type of setup with molecules or formula units. This is the exact same as the last slide. The only difference here is that instead of writing atoms here, I substituted molecules. So this is just converting from moles to molecules and from formula units back into moles. Here's a sample problem. This is like one that you would see in your textbook. It says, how many atoms are in 2.5 moles of silicon? So we always start our problems with what was given in the problem, our known information. So 2.5 moles of Si is what we're going to write first. Then we're going to set up our conversion factor. What we're going to cancel out is going to be on the bottom, and what we want to convert into is going to be on the top. So this is the work that I want to see. 2.5 moles of Si times 6.02 times 10 to the 23rd atoms over 1 mole. Now when you multiply across and divide by the bottom, that will allow your mole units to cancel and will tell us how many atoms of silicon that we have there. This one is doing the exact reverse. So this problem tells us to convert 3.01 times 10 to the 23rd atoms of silicon into moles. So again, start with what we know. We have 3.01 times 10 to the 23rd atoms of silicon. And since we're still dealing with atoms and moles, we want to use Avogadro's constant, but we want to flip the conversion upside down this time. We want to cancel out our atoms units. So atoms needs to go on the bottom, and the 1 mole of silicon needs to go on top of our conversion factor. This will allow our atoms units to cancel and will tell us how many moles that we would have of silicon. These are relative atomic masses, and we've done these ones before. A relative atomic mass is the mass that you're going to see up on the periodic table for an element. It's the weighted average of each isotope's mass. So you need the mass for each of the isotopes and also its percent abundance. It's not a regular average where you just add the numbers together and divide by however many numbers you put into the problem. This one, for instance, takes copper 63 and copper 65, gives us our mass values in AMUs, and also tells us the percent abundance. So you can see that copper 63 is much more abundant in nature than copper 65. So you're going to take the mass in AMUs and multiply that by the percent abundance in decimal form. So 69.17% becomes 0.6917. And then we do the same thing for our second isotope, 64.93 AMUs times 0.3083. And then add those values together. That's going to give us 63.55 AMUs, and that's the value that you'll see for copper's mass up on the periodic table. Now, molar masses are the masses of an entire compound. So far we've only talked about atomic masses being on the periodic table. Those are the masses for one individual atom. Now, molar masses are just adding the masses of individual atoms that are in a compound. So, for instance, with CO2, we're going to need to add up carbon's molar mass from the periodic table, which is 12.01 grams per mole, and oxygen's atomic mass. Now here, we have two of them, and each oxygen from the periodic table tells us that they're 16 grams per mole. So we have to multiply that value by 2 since there are two of them here in this compound. So add those to carbon, and you get 44.01 grams per mole. So that would be the molar mass of CO2. Here's another one. It's a bit more complicated. This one tells us to calculate the molar mass of barium nitrate. Now this has parentheses in it and subscripts and things, so it's going to take a little bit more effort. First, we need to find out how many of each type of atoms we have. So we have one barium. Barium's atomic mass from the periodic table is 137.33 grams per mole. And then because the nitrogen is part of the polyatomic ion in parentheses here, we need to distribute this 2 to the nitrogen. So there are 2 nitrogens, each at 14.01 grams per mole. And now, since we already have 3 oxygens inside here and 2 outside, that means we have to multiply those together. So we're going to have 6 oxygens, each at 16 grams per mole. So if we add up all of those values, then that's going to give us 261.35 grams per mole for the total molar mass of barium nitrate. So we're going to be using those molar masses as another conversion in addition to Avogadro's. So we use Avogadro's if we're dealing with atoms or molecules or formula units. We're going to use molar mass if we're dealing with moles and grams. So here's a problem. I just made up a value, 2.49 moles of potassium fluoride, and I want to find out how many grams that is. For instance, maybe I want to weigh that out in the lab to conduct an experiment. Well, I can't weigh out moles. Okay, so I'm going to use grams. So I'm going to add up a potassium and a fluorine, and together those give me 58.1 grams in every 1 mole of potassium fluoride. And when I multiply those and divide by the 1 mole, that will cancel out my mole units and tell me how many grams of potassium fluoride that would be. I could do the same thing going in reverse. I could take the amount of grams and then convert it into moles by just flipping my molar mass upside down. So for this one, I want to take 110 grams of potassium fluoride and multiply it by 1 and then divide it by 58.1 grams of potassium fluoride. That would allow my grams units to cancel and tell me how many moles that I would have. Here's a sample of a problem like this that you would see in your book. It says, what's the mass in grams of 3.5 moles of copper? So what we know is the 3.5 moles of copper, and if we look on the periodic table, we can also find its atomic mass, which is 63.55 grams in every 1 mole. So this would be the work that I would want to see. 3.5 moles of copper times 63.55 grams in every 1 mole. When you multiply across and divide by the bottom, the mole units will cancel and tell us that that is equivalent to 222 grams of copper. This one is going in the reverse. This time it asks us to determine the number of moles in 237 grams of copper. So our known this time is how many grams we have. We're still using copper, so it's still the same atomic mass at 63.55 grams per mole. And when we multiply by our conversion factor, we're going to do 1 over our 63.55 grams. So that way our grams units will cancel and all that will be left over are moles. So this kind of just sums up all these problems that we're doing. There's only 2 conversion factors. We're either using Avogadro's, that's when you're dealing with atoms or molecules and trying to go to moles, or the reverse. And if you've got moles trying to go to grams or the reverse, then you're going to use the periodic table and get the atomic or molar masses. This is one that involves both steps. So this actually involves Avogadro's and molar masses. So this problem gave us the amount of atoms of boron that we have. They said we have 1.2 times 10 to the 24th atoms of boron. And I want to find out how many grams that is. So the first thing I have to do is convert it into moles. There is no direct conversion straight from atoms to grams. So I want to use Avogadro's constant. And because the atoms is what I want to cancel out, I want to write it as 1 mole over 6.02 times 10 to the 23rd. That'll cancel out my atoms units. And then now that I have it in moles, I'm going to use the molar mass of boron to find out how many grams that would be. So if you look up on the periodic table, boron's atomic mass is 10.81 grams in every 1 mole, and the moles needs to go on the bottom here so that it will cancel. And then the last step will be to just plug it in your calculator. So you want to take everything on the top, multiply it together, and then divide by the bottom. It's best to do these problems in one step as opposed to stopping after this first part, rounding off an answer, then multiplying by the last part and rounding off an answer. By doing that, you're going to get further and further from the true value. So try to do it all in one step. You could do the same thing if you were given grams and we're supposed to go all the way to atoms. It would just go in the reverse order. So you would use your molar mass first to convert to moles, and then use Avogadro's to convert to atoms.